Okay, so for this question, yeah, so I just rearranged the numbers a bit to make it make sense a bit more. Okay, but so why do you think it's continuous? So how do you show it's continuous? Well, you have to find a limit, right? So yes, each of these respectively are continuous on their domains. But where might this not be continuous is you have to think about what's happening at 2. So look at the limit as x approaches 2. If this is continuous, what must this limit be? Right, it must equal f of 2. So first of all, what is f of 2? 4. So you want the limit to equal f of 2. So in a piecewise function, you should look at limits from the left and the right, because this splits to the left and the right of 2. So first of all, what is the limit as x approaches 2 from the right? Which function do I look at? The second, yeah. So 2x squared minus 2. What is that limit? So you plug in 2, this makes 8 minus 2 is 6. So already you know it's not continuous, actually. However, we could also check to see if this limit exists. So I might analyze the type of continuity. What's the limit from 2 to the right? Or to the left? The first, yeah. And what's this limit? 6. So is this continuous? No, it's not continuous. However, the limit does exist. So for this question, the limit exists. The limit as x approaches 2 of f of x exists. F of 2 exists. But the limit as x approaches 2 of f of x does not equal f of 2. So it's not continuous at 2. So even though the limit exists, that doesn't mean it's continuous. But the limit also has to exist and it has to equal what's actually happening at that point. Okay, so this would be like showing your work for that. So if you did it like by graphing or something, I wouldn't like that as much, just because it's not using continuity. So make it like 1 point off, but not a big deal. But so this is the calculus way of showing continuity. Okay, so let's continue where we left off last time, or time before last, because last time was the quiz. So when we last discussed derivatives, we came up with some rules. Can you remember some rules that we had? And you remember the derivative of a constant? Yeah. Yeah, it's 0. Yeah. Why is it 0? Because a constant function means it doesn't change. So derivative is a measure of change. And if it doesn't change, well, of course it's 0. And you remember power rule? It's called the power rule. So you have the derivative of x raised to the nth power, or a number power, right? So, well, so you mean drop the power? Do you mean right as a multiplication? And then minus 1 to the power. Yes. Question. Can you use the power rule on this? Is the power rule applicable there? For 2 to the x, is that power rulable? C. Well, this is a totally different function, right? This is not of the form x to the n, right? Power rule is only for x raised to the nth power, right? 2 raised to the x power is completely different. So we don't know yet how to find this derivative. So this is not power rule. So what is essentially a power function is anything of the form x to a so the main idea is that this is a number. That's the idea. This has to be a number. It can't be a variable. X is a variable, so you cannot use the power rule for a variable exponent. Does that make sense? In Calc 2, you'll deal with finding derivatives of these types of functions. You need like the natural log. Actually, speaking of which also, what is this derivative? Good, yeah, it's 0, right? It's not 2 pi, right? For the power rule, this needs to be a function. Well, we'll call it, this needs to be a variable. Yeah, that is ln of 2 to the x, yeah. But we can't, so we haven't really discussed why, but that will end up being that. Yeah, so let's rewrite. So you can only use power rule when n is a constant or a number, and x is a variable. Okay, yeah, because this is a constant base. Okay, so just things to watch out for. Okay, let's do some more. If I have the derivative of a sum, what is the derivative? Yeah, so it's very nice. You just take the derivative of each. And yeah, another notation, you can write this. So this is the sum rule. And we also had the product rule. How do you take the derivative of a product? Yeah, so you take the derivative of one times the other, and then plus the derivative of the other times the original. So this is the product rule. Okay. Let's do one more that we didn't discuss, but it's almost very trivial. But it's the derivative of a constant times a function. So how do you prove what this is that you need a limit, right? Let's take a limit. So let's do the difference quotient definition. Okay, yeah, so you can treat that as a product, which is fine, but let's prove it using the difference quotient. So when I plug in x plus h here, I get cf plus h, and then minus cf of x over h. And then what can I do after this point? How do we continue this limit? Any ideas? So there was a good guess in the chat that this might be equal to cf prime of x. So knowing that, what do you think you need to do to this to get cf prime? Right now, it's not obvious that it's cf prime. What do you need to do to make it cf prime? Can you simplify this limit? Yes, you can factor out the c. So factoring out the c, you get c times limit as h goes to 0 of f of x plus h minus f of x over h, which is the derivative. Yes. So this is the derivative again. Yes, this is the proof for the constant. So you can call this like the constant rule. Maybe. Well, you need to deal with the limit definition of the derivative for this section. For the first two sections, you have to deal with the limit definition. So this could be a question. So, I mean, just don't be afraid of the limit definition of the derivative, because like with your homework and with maybe the quiz, you'll probably have to deal with the limit definition. So just get comfortable with the limit definition. But I mean, this is a very simple proof for that. But like for other ones like product rule and what we'll later do as quotient rule, those are probably too involved for like a quiz question. But just because we have formulas that we developed for derivatives does not mean that we get to forget about the limit definition. So just make sure you know the limit definition of the derivative. Okay. So we had some other derivatives. Derivatives of some trig functions. And remember what derivative of sine was? Cosine, yeah. How about the derivative of cosine? Yeah, this one was a negative sign. So we had done these previously. So the goal today, and we also did some combinations of sine and cosine a couple classes ago, like with products. The goal today would be, let's finish up the trig functions. Finish derivatives of trig functions. So a natural progression would be to find the derivative of a quotient, right? Because what's the next maybe simpler trig function is tangent. And I mean, you could do it with the limit definition, but it might be more expedient. Yes, it'll eventually be secant squared, but we'll show that. We'll prove that using the quotient rule. So yeah, it might be more expedient, instead of using the limit definition to find the derivative of tangent, would be to develop a quotient rule. So this will be the quotient rule. Okay, so let's prove it. No, not necessarily, right? The product rule doesn't behave that way, right? The derivative of product is not just the derivative of each. So you probably would expect that the derivative of a quotient would not be just the quotient of each, right? So if you think that's true, then you have to go prove it, right? You can't just assume it's true. So let's actually prove it. It might be just to take the derivative of each and divide, but let's actually prove it. It ends up, it's not going to be that, but let's show it. Okay, so it's the limit as x approaches a. So this is the definition of the derivative. You have f of x over g of x minus f of a g of a. And this is divided by x minus a, right? This is the definition of the derivative. Yeah, we'll find out. We'll find out what the quotient rule is. So, okay, how do we simplify this limit? How do you deal? Yeah, good. Common denominator. What is the common denominator? Yes, g of x, g of a. Okay, so what's the result? So you get f of x, g of a, because a g of x and g of x cancel, then minus f of a, g of x, because the g of a cancel. In the denominator, you have x minus a, and then gx, ga. Okay. So what do we want to pop out in this limit? We want this to pop out in this limit. F of x minus f of a over x minus a. And we also want this to pop out. G of x minus g of a over x minus a. We don't quite have that, right? So question, can I add something to this term to give me f of x minus f of a? What do you think? And hint, by factoring. If subtract a term, then I can factor something to give me an f of x minus f of a. So subtract because it's f of x minus f of a. Not g of a g of x, but f of a g of x. Right? The g of x allows you to factor that out and then just be left over with f of x minus f of a. You see that? So now the g of x is factorable, and then you have f of x minus f of a. So we know that if you subtract something, you better add it, because then you'll break math. So add f of a g of x. Right? Because I can't just magically subtract something. But this is nice, because now it just happens to work out that the g of x can get factored here, and then I get, oh, sorry, not the g of x, the, wait, I'm sorry, this is, my bad. This is g of a. I miswrote it. So this should be g of a. Oops. Sorry about that. Miscopied. This is g of a. All right, so now it makes sense that f of a can get factored out. Everyone see that? Okay, so let's split up this fraction into these nice derivative components. So we have f of x minus f of a, and then factored g of a. And then plus f of a times g of a minus g of x. So then they're both x over a, g of x, g of a, and of course there's a limit here. X minus a, g of x, g of a. Okay, so now take the limit. What does this simplify to? So this is what? With the limit. This, well, maybe you have to do something with this one first. But what's this with the limit? The Boxton portion. F prime of a, but yeah. F prime of a, g of a, and the denominator is g of a squared. And I'm going to leave it as g of a squared for now. But this one is a little bit different, right? Is with the limit, is this the derivative of a, of g at a? Does it look kind of awkward? It doesn't look exactly like this, right? What's different about these two expressions that are boxed? Yeah, they're different, and in particular the signs, right? So because they're different, do we give up, or can we do something to turn this into that? How do we change the sign? How do you turn, yeah, what is it off by? It's not g prime of a, right? Because this one is g of a minus g of x, but not g of x minus g of a. But I can do something to turn it into g of x minus g of a. How do you switch the sign of a subtraction? Yeah, so instead of multiply by -1, factor by -1, because you don't want to change anything. So if you factor by -1, then you get the derivative. And then when you take the limit, you get g of a squared. Okay, so the reason why I didn't cancel out this factor is because I want to have a common denominator. And then we get f prime of a, g of a, minus, usually it's written like this, g prime of a, f of a, over g of a squared. So this is the derivative at a. So another formulation of this, if you don't want to write out all the x's and a's, is f prime g is, or f over g prime is f prime g minus g prime f over g squared. Okay, so any questions about that? This is the quotient rule. All right, so some things to watch out for. The numerator looks very similar to the product rule, right? Except it's a subtraction instead of a plus. And the biggest thing to watch out for is that which derivative do you write first? You write the numerator's derivative first. So that is the derivative that comes first, the numerator's derivative. So it's kind of how I like to remember it. As long as you remember to do the derivative of the numerator first, then you're good. And then it just looks like the product rule, but with the subtraction. Any questions about that? So this is a thing you probably should memorize along with the other derivative rules, because it would be kind of a pain to prove this, of course, if you forget. Okay, questions? So remember the step was factor by -1. Okay, so let's apply this. So now we know how to take the derivative of tangent. Okay, so I'll write the derivative again of the quotient. Okay, so let's do it. So you take the derivative of the numerator first. times the denominator minus the derivative of the denominator times the numerator, and divided by the denominator squared. Not quite that, because you forgot to take the derivatives, right? So what's the derivative of sine? It's cosine. So right, instead of cosine sine, it's actually cosine squared. And then what's the derivative of cosine? Is positive sine, so we get a plus here. You see that? Good. So what does the numerator become? This is an identity rule. Which identity rule is it? It's equal to something. Yes, it's a Pythagorean identity. Correct, it's 1. Right, this looks a lot like the Pythagorean formula. Okay, and then what's 1 over cosine squared? Yes, secant squared. Okay, so the derivative of tangent is secant squared. So how I like to, when you first start doing the derivatives of trig functions, I highly recommend don't waste your time memorizing the derivative of tangent. Whenever you see tangent, just go ahead and do the quotient rule every time. Because A, it's good practice for the quotient rule, and B, as you do it more and more times, then you'll memorize it naturally as secant squared. So that's just my tip for learning math, is don't go straight to memorizing. Do it first, and then memorizing, it just becomes, natural. Okay. It's easier to memorize something that makes sense, right? Otherwise, you're just memorizing symbols and you don't know what they mean. Okay, so let's do the same thing for cotangent. So it's just the flip. So again, you do derivative of numerator times denominator minus the derivative of the denominator times the numerator divided by the denominator squared. Okay, so what's the derivative of cosine? Oh yes, negative sine. Thanks. So negative sine squared. And then minus, and then what's the derivative of sine? Cosine. Yep. And then what does the numerator become? Can you simplify the numerator? There's an identity in the numerator. Hint is to factor something out. What's a common factor? Yes, -1. So you factor out a negative, then you get the Pythagorean identity. So then you get -1 over sine squared. And what's -1 over sine squared? Yep, negative cosecant squared. Okay, so that is the derivative of cotangent. The derivative of cotangent is negative cosecant squared. And again, before you go right to memorizing, just do this quotient rule out every time first. Okay, questions about that one? Yeah, we'll find that out. That is something we will see after we do all of these. So yeah, so at the end of doing all the derivatives of the trig functions, well, we don't know that cheat code exists yet, right? So like we don't know anything yet. So, feign ignorance, until we get to the chart of all the derivatives. So right now we don't know anything, but we'll see that like all these co-functions have negative derivatives, and they all involve sine somehow, but not yet. Okay, how about secant? What is secant? Yeah, 1 over cosine. Okay, so let's do the derivative. Okay, what's the derivative of 1? Yep. And what's the derivative of cosine? Negative sine. Good. So what do we get? We get 0 and then plus sine, because we have a minus minus. Okay, so can you simplify this? Sine over cosine squared. It'll be too complicated to rewrite cosine as 1 minus sine squared. So can you express this as a product of two trig functions with 1 power? Good, cosine, cosine. Okay, good, tangent over cosine. And then what is tangent over cosine? What's the cosine in the denominator? What's 1 over cosine? Yeah, so it's secant tangent. So the derivative of secant is equal to secant times tangent. Okay. Questions about that one? All right, let's keep going. What's the last one that we haven't done yet? We haven't done cosecant. What's cosecant again? It's 1 over sine. Okay, so let's do it. Derivative of 1 is 0. So 0 times anything is 0. Minus the derivative of sine is cosine times 1. And then over sine squared. So how do we simplify this? Yep, we have a cotangent for the cosine over sine, and then we have left over 1 over sine. So we get cosecant cotangent. So the derivative of cosecant is negative cosecant cotangent. Okay, so now let's make a chart and then maybe see some connections. Again, I recommend just doing this out every time until you naturally have it memorized. Okay, so what's derivative of sine? It's cosine. What's the derivative of cosine? Negative sine. What is the derivative of tangent? Secant squared. Derivative of cotangent? Yeah, negative cosecant squared. Derivative of secant? Yep, secant tangent. And then derivative of cosecant? Negative cosecant cotangent. So notice that the derivative of cofunction always has a negative, and it deals somehow with sine, right? Sine is the derivative of cosine is negative sine. Cosecant is 1 over sine. So all the derivatives of cos have a negative, and they have a sine pop up somewhere. So all the ones that are not co are all positive derivatives, and they all deal with a cosine. So, right, it's positive, so this is cosine. Secant is just 1 over cosine, and then secant is 1 over cosine. And then if you look at the rows, there's another similarity. The derivative of the sine functions are just the other sine function. The derivative of the tangent functions are the secant functions. And the derivative of the secant functions are the secant tangent functions. So that could just be a little rule for you. But again, I really recommend you do the quotient rule to memorize, to just get the habit of doing quotient and understand. It will help you understand what tangent, cotangent, secant, and cosecant are, and those derivatives. Any questions? Did everyone see the relationships? It's very surface level, but it's maybe a nice pattern. Okay. Questions? Okay, so let's move on. So let's talk about, let's go backwards and start talking about the tangent line again. So what is special about the tangent line in calculus? What was so special about the tangent line? Someone give a... right. The tangent line was kind of like the center of all calculus here, right? So secant... Yeah, so the secant line is the line between 2 points. Yeah, so the tangent line is the limit of the secant lines. Right, limit of secant lines. Yeah, so, and how does this tangent line relate to the derivative? Is exactly right. The derivative is precisely the slope of at the point is defined as the tangent, the slope of the tangent line at the point. Defined as slope of tangent line at the point. Question mark? What's your question? That is the definition of the derivative. It's the geometric one. It's a slope of the tangent line. Yeah. So when we first started talking about the derivative, that's how we defined the derivative. So if you have a and f of a, f prime of a is the slope of that line. Okay, so if you have the slope of a line, you have a lot of information about the line. So this topic we don't really actually need to do because everyone should know this already. But we'll do it anyway. Okay, so what 2 pieces of information do you need for the equation of a line? So given so how do you to determine what the equation of a line, what 2 pieces of information do you need? Slope, intercept. Okay, but how about something else? Intercept might be hard to see, and intercept is a specific point. Yeah, so you don't need the y-intercept. All you need is just any point. So the y-intercept is a specific point, but any point will do. Right. And remember what equation of a line? There's 2, maybe 3 main equations of a line. Which equation or form of equation is the best one for these pieces of information? it's called point slope form. Yeah, but that should be an equal sign, right? It's y minus y1 equals mx minus x1. Yeah, so it's called point slope form because you have a point and you have a slope. Okay, so if I have a tangent line, I know what the slope is, right? What's the slope again? Slope of the tangent line? Secant squared. That's tangent, the function. That's different from the tangent line. They have similar names for a reason, but yeah, not tangent as the trig function. What is the slope of this line? Yeah, the derivative where? Derivative at what point? Specifically, where is the derivative? Is it the derivative here at this point? Is the derivative at this point? At a, yes. So what is m? Is the derivative at a. Okay. What's x1, y1? You know a point. So this is why we use the point slope form and not the slope intercept, because maybe I don't know what the intercept is. But I know what point I can use. What point can I use? Yep, a f of a. Yeah, that's exactly this right here. Oops. A and f of a. And the slope of this line is f prime of a. So that's it. That's the equation of a tangent line at a point. Okay, so any questions about that? So again, there's nothing new here, right? This is just kind of using information that we know about the derivative. Okay. So let's do an example. So let's start easy and have f of x is equal to x squared at x equals, let's do -2. Okay, so what two pieces of information do I need for the equation of the tangent line? Sure, we can do the point first. So let's do the point and let's do the slope. So how do you find the point of the equation line at x equals -2? What's the point that I can use? So point is two things, right? It's an x and a y. So yes, it's -2, -2, -4. So the point is -2 f of -2. So it's -2, and then -2 squared is 4. Good. Okay, how do you find the slope? slope. When in doubt, if you're in a calculus course, what should you do? Yeah, probably the derivative. Yeah, the slope is f prime of -2. Okay, so what is f prime? Two x. And then what's f prime of -2? -4. Okay, so let's put it all together. So y minus, what is it? Yep, y minus 4 equals what? So m goes here, right? Yes, so -2x plus 2. So -4, and then x minus -2, which is plus 2. Okay, so we can simplify that if we want. We have y minus 4 is equal to -4 x plus 2. So this is y minus 4 equals -4x minus 8. And y is equal to -4x minus 4. Okay, so any questions about that? So, by the way, it's good to check to make sure your answer makes sense. You know the derivative should be negative because, when you draw it, which you should know how to draw x squared, it has a negative slope. All right. Questions? All right. Let's go on. Let's do equation of tangent line for f of x is equal to, we like this way better than limits. Well, we're doing limits here, right? We did a limit, but we just kept a couple steps. The limit is the true definition. What do you mean derivatives make it easier? Derivatives are limits, right? When you're doing a derivative, you're doing a limit. So they're the same. But you should really appreciate the limit definition, right? Because this whole deal of this makes no sense, right? If you just look at that, that makes no sense. But now that you know where it came from, right? You had the limit of the slopes of secant lines, and you developed that, and then you appreciate that more, right? Otherwise, you're just memorizing, baseless facts. Right? But you need to know this, right? You need to know why this is true. They're not different approaches, right? This is the same approach as the limit definition. But we just establish that this is something you can do by doing the limit. You can't just say this without any reasoning, right? You can't just state facts without knowing why they're true, right? just a little to appreciate the math. It's not just a bunch of facts, but there are reasons. Yeah. Okay, so let's do tangent. So yes, tangent line at tangent. That's of tangent. It's a mouthful, but at negative pi over 4. So negative pi over 4. Yeah, that's true. I guess the nice thing about derivatives is that once you establish all these rules, you can really find the derivative of many things very quickly. So that is nice about developing all these formulas. So in that regard, yeah, it's a bit nicer. Okay. Okay, so let's do this question. So what are the two things we need? We need a point and a slope. Okay. So what is a point we can use? The only point that exists here. Yeah, so it's negative pi over 4, comma, tangent of negative pi over 4. And good, remember it's negative 1. And let's just remind everyone else why it's negative 1. So negative pi over 4 is in the fourth quadrant. And the pi over 4s are the nice ones where the x equals the y. But in the fourth quadrant, the y is negative of. And then in y is x equals y nice for tangent is because tangent is x divided by y. So you have the same thing, but one's negative, so that's why it's negative 1. Okay. And then how about the slope? How do you find the slope? Yes, so you need to find the derivative at negative pi over 4. So the derivative is secant squared, and then you plug in negative pi over 4. So this is secant squared of negative pi over 4. Anyone know what that is? You don't have to memorize this because it's all just sine and cosine in the end, right? Which one is secant? It's 1 over what? Yeah, I think it'll be 2, but yes. So it's 1 over cosine squared. And then what's cosine of negative pi over 4? What's this one right here? It's radical 2 over 2. You square that, and you get 1 over 2 over 4, which yes is 2. Okay. So what is the equation? It's y minus negative 1 equals 2 times x minus negative pi over 4. Okay. So rewriting that, it's y plus 1 is equal to 2x plus pi over 2. So y is equal to 2x plus pi over 2 minus 1, or if you really want to be fancy, 2x plus pi minus 2 over 2. Okay, questions about this one? Okay. Let's do tangent at 0. Okay, so I'm not going to draw anything. Let's just fill in the dots. So what is a point of tangent of x? What's the point I can use? Origin, right? Because tangent of 0 is 0. Right? And then what's the derivative? Or I said it already. The slope of the tangent line is the derivative at 0. So what is secant squared of 0? Right, 1. And then x minus 0. So I think it's an interesting fact is that the tangent line of tangent at 0 is just y equals x. So it's just like a diagonal line. So one way to think about the tangent line, which you'll talk more in Calc 2, is that the tangent line and the derivative in general, it kind of tells you an approximation of the function, like at points. So if you zoom in at 0, just keep on zooming in. What is tangent going to look like as when you zoom in and zoom in closer and closer to 0? It's going to look a lot like this flat line y equals x. So what's very cool about derivatives is that it's kind of what's called like a linear approximation. Right? Linear functions are very easy to work with, right? They're just lines. So one way to think about the derivative and why it's useful, it's like it approximates tangent at around, not at, but around 0. So we'll do this actually later when we do differentials. So if you want to calculate, let's say you want to calculate tangent of, this is skipping ahead, but just thought about it, so it's nice to think about. Tangent of 0.001, if you plug that into the calculator, it's probably going to be very close to 0.001. Because for the very reason that tangent is a lot like y equals x. So something to think about, like, why do we care about the equation of a tangent line? Well, we'll find out later that it allows us to kind of get very approximate values. So And we kind of get the idea there, like kind of the purpose of what we're of this derivative and tangent lines. Kind of gives you a behavior around a point in a function. So we'll do it later, but it just popped up. Okay, so let's continue on with some more trig functions. Okay, how about sine? What's the point? And what's the slope? Yep, it's also the origin, 0 sine of 0, which is 0, 0. And the slope is 1 because the derivative is cosine. And the derivative at 0 is 1. So what is the equation? It's also y equals x. So another kind of cool fact is that sine and tangent are very close to each other at 0, around 0. It looks like what tangent looks like around 0. It's kind of a cool fact. And actually, when we're going to do the same thing for cosine, and maybe you can see why that might be true. Okay, what's the point that we can use? Yep, 0, 1. 0 comma cosine of 0. And what's the derivative of cosine? Well, the derivative of cosine is negative sine. And then when you plug in 0, yes, you get 0. Now, what's the equation of the tangent line? Let's write it out. Y minus what? Yep, y minus 1 equals, what's m? 0 times x minus 0. So what's the equation of the tangent line? Y equals 1. And why is this not surprising? Because at 0, there's a peak in cosine. So it flattens out at 1. And just a little fun thing to see. The equation of tangent line at 0 for sine was y equals x. The equation for the tangent line of cosine at y equals 0, x equals 0 is y equals 1. And then for tangent was y equals x. So it's kind of like x over 1. So it may not always be true, but it was true for this one. Okay, so something to note was cosine is the derivative of sine. So what we found was the equation of the tangent line for the derivative of sine at x equals 0. So in that same vein, let's keep on go. Let's find more derivatives of sine. Okay, I'm not sure if I introduced the symbol yet, but so d dx is the derivative, and then d squared over dx squared is the second derivative. Can someone remind me what the second derivative is? What does that mean, the second derivative? Yeah, it's the derivative of the derivative. So understanding that, derivative of the derivative, d squared dx squared of sine, you can think of that as the derivative of the derivative. Yeah, so it will be negative sine. The derivative of sine is cosine, and then the derivative of cosine is negative sine. Okay, so let's do the tangent line. And let's also do x equals 0. Okay, so what's the point? So this is my function. What's the point I can use? Yep, 0, 0. Right, negative sine of 0 is 0. And what's the slope? What's the derivative of negative sine? Derivative of negative sine? Use the constant rule. Take the negative out. So what is the derivative of negative sine? Yep, negative cosine. Okay, so what happens when you plug in 0? Negative 1. So what is the equation of the line? Y minus 0 is equal to negative 1, x minus 0. So y is equal to negative x. So let's just see the picture. This is negative sine. And this is the tangent line. Y is equal to negative x. Okay, any questions? Just a few of you are participating, but maybe like one or two. So I'm not sure what other people are thinking. How is this feeling? Just quiet today? Yeah, it's late. I understand. Okay. Okay, so I'll just keep on moving on. But of course, if you have questions, please stop me. Okay. Okay, so let's yeah, I think once we establish the rules of the derivative, then the application is it's a bit better than the limits. Okay, so let's take more derivatives. So if there's a 3 there, it's the third derivative. So it's the derivative of the derivative of the derivative. So in physics, if position is no derivative, if velocity is the derivative and acceleration is the second derivative, last class someone suggested the third derivative was it's called jerk. I think I remember that to be true. But I think once you get further and further down the derivatives, they get less and less applicable. They exist, of course, but they get less kind of needed at the more derivatives you go down, because it might be they might be constant at some point. But at least for the third derivative, there is something called jerk. It's the change of acceleration. So, okay, so let's think about that. What is the third derivative of sine? So based on our definition of the higher derivatives, it's just that you just take the derivative of the one before. So our second derivative for sine was negative sine. So yeah, so the derivative after that is just negative cosine. Remember, this is using the constant rule by taking this out. Okay. So let's find this equation of the tangent line. For the third derivative, at x equals 0. Okay, so what's the point we can use? So you're plugging it into negative cosine. So what's cosine of 0? Yeah, so what's negative of that? Negative 1. Okay, good. So what's the slope? So what's the derivative of negative cosine? Positive sign, yeah, there's negative, negative. And then what happens when you plug in 0? 0. So the equation is y minus -1 is equal to 0 times x minus 0. So it's y equals -1. So by the picture, this is negative cosine. And then at -1, it is like the valley. So it's flat there. And why is it y equals -1? Because that's this line. Okay, any questions on this? All right, so let's keep going. So the fourth derivative is just as what you expect. 5-minute break. We're almost done. Just need a breather. All right, I'll slow down. So I'll just set this up. Sure, you can take a break. Okay, yeah, sure, we can start back up again. 9:12 or something. Which I was thinking about that. If you want, would you like a short break? So this is a long class. Maybe a short break would be nice. Maybe in the future we can do short breaks. Figure out a good time for that. Okay, so let's take a short break. If you don't want to take a break, think about what I'm trying to show here, and why am I taking higher derivatives? Something's going on here. But in the meantime, if you have questions, please let me know. No, this is kind of jumping around a bit. This is section 3 or 4. We finished 2.1 and 2.2. I believe the tangent lines are part of 2.3. Oh, the grades. So by the weekend, I'll be able to work on it, and I'll post it on probably on Blackboard. If not, I mean, you can kind of estimate. Yeah, so I'll probably get on Blackboard. But you should know it, what your grade is pretty closely, based on Lumen should have given you the grade. But it might be plus a few or minus a few, depending on if you got partial credit or minus credit for incorrect work. Messy work. I mean, I'll try to make it out. I've seen messy work. So I'm not going to be like too harsh on taking points off. So I mean, whatever your grade is on Lumen, it's probably closer to that. If anything, I'd be more forgiving with partial credit than I would be with taking off credit. You know, I'll take off credit if you like plugged stuff in for limits instead of actually doing the limit. Some stuff like that. I've used, or if it doesn't look like you knew what you were doing, or just memorize something, or God forbid you look something up. But I wouldn't worry too much about it. So no, it wouldn't be that far of a drop. At most, it'd be like plus or minus 3, or minus 3, but it could be plus more. Yeah, I wouldn't take off too much. Like max, I would take off as 1 per question for work, and I'd add like for partial credit. Like I could give up to full credit if it's like good work, because the Lumen is just like a yes is binary, right? Which it's kind of a hard way to assess someone just by a yes or a no. So that's why I like doing partial credit. All right, it's been 5 minutes. Okay, so let's finish this up. So we're getting close to something cool here. What's the answer to this? What's the fourth derivative of sine? Sine, yeah. Isn't that cool? Why is that cool? It's because what if you take 4 more derivatives? What do you think you'll get? Yeah. Yeah. So this means that d8 dx to the fourth, or no, not fourth. This does not make any sense here. d8 dx to the 8 of sine is sine. Okay, so something's going on here, right? So based on that, so if d8 dx to the 8th of sine is sine, what do you think d9 dx to the 9th is? Cosine, yeah. What do you think d10 is? Negative sine. d11. Negative cosine, yeah. And d12. Back to sine. Okay. How about d to the 173? Yeah, it's looping. So the first derivative is cosine. The second derivative is negative sine. That 2 looks a lot like a 1. The third derivative is negative cosine. And the fourth derivative is sine. So what do you think the 173rd derivative is? What do you think you would need to do? Why is it negative cosine? I don't know, but are you just guessing, or? Oh, well, not by odd number, right? Because notice that it could be one or the other. So it's not just odd and even. Negative sign. Well, what's your method, right? Are you guessing, or what's your method? If something loops every 4 times, why was 12? You need to find how many 4s in 173. How do you do that? And then it's leftover. What's precisely what are you doing there? That's an operation you're doing. How do you determine how many 4s in 173? Yes, you're dividing by 4, and then you're finding the remainder. Okay, so what is this? 4 into 17 goes 4 times. 4 into 13, was that 3 times? Remainder 1. So the remainder, so it's cosine. And you see the idea there? So you're doing 43 loops, and then you do 1 left over. It's kind of cool, right? Oh yeah, you're talking about I squared is -1, I cubed is -I to the 4th is 1, and then I to the 5th. Yeah, that's a similar idea. Yeah, so insofar as there's a looping going on. Yeah. There's a reason. It's actually kind of is tied with the sine and cosine, but it's something you might find out a lot later. Okay, so let's do the same thing. For cosine. Do I have to find a whole nother loop for cosine? Why or why not? Do I have to loop all over again to determine the loops of cosine? No. Why? Because this is just the derivative of sine. So it's actually that. So if we just do one of them, we can you can get the rest. So what should this be? It should be, the remainder should be 2, right? If this remainder was 1, if you do 1 more, it would be remainder 2. So that would be negative sign. So just kind of a neat fact. So if you want to characterize this, so, of what? Of sine. So if you like formulas, then this would be a formula. It would be sine if n not sure if anyone knows this notation, but this just means k mod 4 means remainder k when dividing by 4. Someone in the last class said that this was an alternative notation with the percent sign. I haven't heard of that, but like if n percent sine 4 is equal to 0, whatever that means. So then what's next is cosine. If when you divide by 4 you get 1 remainder, you get negative sign. If when you divide by 4 you get 2, or when you divide by 4 you get 3 for negative cosine. Okay, yeah, so it's just a neat formula for the derivatives of sine. When you get to Calc 2, this will be very handy. Knowing higher derivatives of functions is very handy for approximation theory. But that is much later. But yeah, so any questions about this? For right now, this is kind of like the only function we have that's really nice. So it's not because sine and cosine are periodic. Tan is periodic, but doesn't have this nice property. There are some functions that you can very easily find formulas for their higher derivatives. When I taught Calc 2, I had this as an exercise. We haven't done this yet, or we won't, but you can find a formula for x times ln of x. This actually, you can make a formula. But some functions are nice, and some functions are not so nice. Here's a nice one. If you have a polynomial, and the degree of the polynomial is less than n, what do you think the nth derivative is? So remember what the degree of a polynomial is? The degree just means the highest x power. Highest non-zero coefficient x power. What do you think the nth derivative is? Here, I'll give you a hint. what do you think the third derivative of x squared is? Last thing we'll do, and then we'll be done. So, well, hold on. I think you went too fast. So the first derivative is 2x, right? The first derivative is 2x. The second derivative is what? Yeah, it's actually going to be 0. So the second derivative is 2, and the third derivative is 0. And then what's the fourth derivative? Also 0. Yeah, so, sorry, these should be x squareds. So if you take high derivatives of polynomials, you'll always eventually get 0. Right? So if you take more derivatives than there are in the degree of the polynomial, eventually all of the powers will end up being 0, because you always subtract 1 to powers in a polynomial. So that's just a fun fact. But okay, I'll see you on Monday, Monday. And you have homework, so take a look at that. I'll be around for questions if you have them, and I will stop recording.